Thank you very much. Oh, yeah, my voice is obviously slightly more loud. So that's the first time in my life, actually, that I have been introduced by two nice ladies. Thank you. And, well, it's the first time for me to do something like a talk in a cafe to a mixed audience, I guess. Some of the people I've seen here, some of the people I've never seen. It's quite interesting for me as well. So, what are we going to do today? And, well, the title is New Ways to Catch Some Rays, and I think the title has been made by Sharon. She's hiding somewhere here. Sharon. Oh, there she is. Thanks for that catchy title. So, I think, I mean, this is a very relaxed atmosphere, and I like it, you know, in such a way.
Good evening, ladies and gentlemen. Our film is starting in Packard Theatre soon. If you can make your way up. Thank you.
Thanks. So, I think I would like to start on a more global scale. So I think energy is very important, and I'll give you some reasons for that. Even I think it's completely unnecessary to actually emphasize that it's very important. It should be clear to everybody. And I will, well, actually, we have something like a table of contents here. So this is a kind of table of contents. Give you an introduction, importance of energy and ways to generate energy. I mean, you know that each single way to generate energy would be a talk of its own. Actually, each line here could be a talk of its own. So you have to excuse me that I can't tell you everything I know, which might be not even that much, but not even that what I know in the 25 minutes. I would like to talk about what challenges we have here and how we try to, well, find solutions for them within the SFI SSC solar energy conversion. And then I kind of focus down to the light harvesting part. So this is then true to the title. I would like to talk about, well, how can we harvest energy from, well, solar energy in particular. Are there new ways how we can do that? Are there new types of biomimetic solar cells, for example? And then the most important part is actually on your side. This is the discussion. So the whole thing here doesn't make any sense if you don't have a good discussion at the very end or even the middle. So if you feel that there's an important question right while I'm talking, you know, don't hesitate, just stop me and I try to give you an answer. Or somebody else here in the room might be able to give you an answer. So let's start. I hope I haven't spoken already 25 minutes. So first, the importance. Well, I could read that to you, I don't do that. Well, first reason, not even that's the most important, but global climate. We are going down a dangerous path, and even some Western countries recently have changed their opinion. They have said some years ago that they don't believe in global warming and all the catastrophes which might be associated to that. I think that's a very important thing. The second reason here is, well, a little bit of a political one. Obviously, some countries, even in the Western world, are ready to make a war. Just, obviously, there were not too many weapons of mass destruction. So, obviously, it was about the oil. And so there's a certain risk associated with actually energy and resources which are connected to that topic. And then the third thing, which is here on the agenda, is actually, obviously, we are all very dependent on the energy. Okay, that means all of us on a daily basis use facilities which use up a lot of energy, and I thought actually that I could encourage you to save energy, which I think is the most precious source we have, because we're overusing the energy usage. Just minutes ago, actually, somebody talked to me and said, okay, you're flying on it every second weekend back to Germany. I said, yes, so my carbon footprint is very awful just because of that. So I'm not in a position to say, behave better, but I think we all have to go back and think what we can actually do in order to save energy. Anyway, this talk is not about the saving, the talk is about potential solutions. This is not a projection of the worldwide energy consumption. This is up to 2004. And you see that the nice categories here, we even have a pointer. Coal, oil, gas, nuclear, hydro, combustible, renewable, and others. And you see others don't play any role at that projection. Well, it's not even projection, that's a past. But you see that in 2004 we had a mix which is practically driven by coal, oil, and gas up to this point. So these are non-renewable energies, and we use up all the resources we have, which needed million years to build up in just several 10 years. This is something we can't allow actually to happen. Even I drive a car on a daily basis, but we have to stop that. There's no other way to think slightly different. But apart from that, can we replace some of the, well, combustion gas produced processes here by more smart ways. Anyway, this is now the projection to the year 2050. If we just continue to do what we're doing, this is 1970, 4 billion people worldwide using 100 million. BOE, by the way, is barrel oil equivalents, so these are just equivalents of 1 barrel oil. 100 million in 1970 for 4 billion people, then 6.5 billion people already have twice as much. And the 9 billion people, the projection for 2050 is 400 million plus. So this is the drama. Actually, no, this is too much. We have to think about how to stop that. And we have to replace some of the classical conventional energy forms by new ones. So this is actually about the energy challenge. This is now telling you these are different countries and their energy usage. This scale is the primary energy per capita, and this is the CO2 per capita. You see, in most of the cases, this is practically linear, it goes up. But there is one tiny exception. This is precisely here. This is France. The reason for that is it's nuclear power. Well, nuclear power has its own difficulties, but it doesn't add to the combustion gas problem. So the CO2 production of the nuclear power is, of course, much better than burning oil or coal, or even peat, to talk about that. Anyway, so we have to get rid of the oil. And, okay, this is the future global energy inventory. And, okay, this is what could be harvested in a best scenario. Okay, so we can have a look. What is the need in the moment? Our need globally is 18 terawatts. This is what we need in the moment, 18 terawatts. And this is actually the projection, what can be harvested if we make it fully usable. This is hydro, the limit is 0.7 terawatt. There's wind, that's class 3, special class, and 10 meters above ground, that's 2.1 terawatt. Nuclear power, 8,000 new nuclear power plants would be just 8 terawatt, and biomass would be 5 to 7 terawatt. So you might see easily that actually you don't get 18 terawatt by any of them singly. So you need a mix, or you actually go for solar harvesting. And the solar harvesting this is what is impinging on Earth here. Solar energy is 120,000 terawatts. Of that, 800 terawatts landmass. This is, a decent factor above. But nobody, of course, tells you that we have to, cover all the surface by solar cells. But it's interesting that solar cell is obviously the only single source which can actually give us as much energy if we're talking about a non-conventional source. This is now the solar spectrum. This is what the sun is delivering to us. The solar spectrum can be nicely described with this equation. That's just the equation, Planck's equation of a black body radiator. And this is now the wavelength distribution. So this here, 500 is green, like my laser pointer. So slightly before and slightly behind that, this is the visible range here. And the rest is near infrared and a little bit in UV. But you see it peaks in the green. And this is now all the energy which is impinging on Earth now versus the wavelengths distribution. And you see actually that there are a lot of absorptions in the atmosphere. And that's also the reason you can't just deal with a typical solar spectrum. So it depends where you are and how much atmosphere is between you. But that's maybe not that important. The second point is this is actually a German slide. I apologize for that, but it was looking so nice. I give you the translation straight away. This is telling you how much energy is created. It's 63 megawatts per square meter solar surface on the sun. And on the radius, on the distance of the Earth per square meter again, it's 1.37 kilowatt per square meter. This is what you can potentially harvest. The point is here, this is the so-called solar constant. So if you do a calculation, you can say, okay, on average, this is the amount of energy which impinges on a square meter. So this is what we can harvest, and this is now the result. So in order to harvest the 18 terawatts which are needed in the moment, you have seen the projections. The projections say it goes up in the future, but for the moment, just the black spots here, here, and here, would be sufficient to harvest all the energy by solar cells. You see, used by this calculation is current devices. So 10% for photovoltaic cells. This is for the single crystal ones actually conservative. They go up above 20%. And it means that we just cover 1.8% of the total land area. Okay, that sounds very positive. I mean, 1.8% of the total area is still a huge area. I mean, I'm not denying that. But you can do that with solar power. There's nearly no other way how you can generate the 80 terawatts by a single other technique. So, challenges. We need to reduce the use of fossil fuel, CO2, and, well, we need to counteract the climate and greenhouse effects here. There are certain challenges. I mean, we are all aware, for example, that solar cells can only work, well, at day, and not always an island, but you will be surprised how much energy you can even harvest an island there. But of course, what you need if you want to make usage of such technologies, you need energy storage facilities. And that sounds more simple than it actually is, because energy storage is a critical thing. So if you would be able to store energy easily, you know the problems with the cars, for example, that the cars are hybrid cars and you have a big battery in the back which is very heavy, and associated problems. So energy storage is very, very important. We come back to that. And energy distribution, of course, as well, but at least, well, we are here on an island, but on the continent it's easier because the different countries can share and can actually distribute the power, ignoring the boundaries of the countries. Well, I want to emphasize still, we need one solution to this energy saving. We can't just run around with the SUVs and just have a 20 liters per 100 kilometer usage of fuel. This is something, I mean, we are burning all the energy from, for the next generation. There won't be any conventional energy form left over in 50 years, and I think we have to change that. So, I would like to introduce now what we try now to do against that. This is an SFI-funded strategic research cluster with a nice name, Solar Energy Conversion. The lead PI is Professor Dominic Zerulla. And we have started in December 2007. So this is an integration of 19 experts from all range of disciplines: engineering, physics, chemistry, and the Conway Institute for Biochemistry. There are 3 universities. Part of is UCD, it's University of Limerick, and it's DCU. So it's mostly based in Dublin here. And the whole cluster will grow to roughly 25 PhD students and 10 postdoctoral researchers over the next 5 years. So this is now maybe the standpoint, what topics are part of that cluster. On the right-hand side, you see all the partners. There are the 3 universities, and there are 3 companies, actually, which do development in this direction. And you see organometallic and composite materials, biochemistry, functional support, microelectronics and optics, metal oxide synthesis, quantum and classical atomic modeling. So there are a lot of experts working in quite different fields and trying to join together to make, well, new technology possible. And these are the 3 main strands. So the 3 main strands contain solar power generation. This is actually just the thing I'm talking to you today, if I'm quick enough to do that. We try to develop inexpensive materials for photoresponsive cells. So the trick is to get rid of the very, very high-priced silicon single crystals. That's very expensive, and therefore even if we generate photo cells with half the efficiency, but at a tenth of the price, that would be very beneficial. So strand 2 is hydrogen generation, and strand 3 is actually solar CO2 conversion. It means by means of catalytic reactions, we fix CO2 at low temperatures and pressures. That's very important, and this can be then burned again, potentially. So you generate your own fuels, make a kind of a cycle. And then the 4th strand is just a translation of knowledge, but we're at a very early stage. So now I'm going to talk a little bit about the solar energy conversion here. So how does it work? Nature is doing that for millions of years. Each green leaf, you have seen that maybe on the first slide, this is a good example. What does it do? This is a very simplified reaction. CO2 and water give a sugar, oxygen and water again. So what you actually generate is these NHDPH. This is something which the metabolism in nature wants to have. And this can be then used in such a way. This is slightly a simplification. This is even a simplification still, but shows the complexity of nature. There are actually 2 photosystems, 1 and 2, and the whole change of redox reactions. And the structure of the antenna complex is actually looking like this. So if you understand everything and you are able to synthesize everything, you can mimic that. But it's difficult. So the most biomimetic ideas take just one aspect out of this complex chain and try to use it. So you make a synthesis between well-known technology and an idea from nature. And this is what we try to do. All right, first, before we make this transition, this is a traditional solar cell. And I speak about that just for a minute in order to show you the similarities. So there's light impinging. This is actually the band structure here. Okay, photons are absorbed in that region. The photons give rise to an excitation of electron in this diffusion zone here. And then when these electrons are able to go down here in the band structure, they can be harvested. So there is a diode function which only allows the electrons to move in one direction. At the moment they have crossed the barrier, they are safe on the other side and we can use them for an electric current. I know that's a simplification, but maybe that's the best way we can express that. And now we try to make a kind of synthesis between this and an idea of nature. And okay, this is the structure of its classical one. There were some basic things, and this is the P-type and N-type semiconductors. This is exactly what you've seen as a band structure. And then you have a lot of helping, supporting layers, you know, anti-reflection coatings and just protective coatings and other things here. So I would like to talk now in the remaining minutes about the Dyesensitized solar cell. So it's named after the inventor Michael Graetzel from the EPFL in Lausanne. Well, Graetzel. And you know, the idea is this cell type converts the impinging photons directly into an electric current. So it's very near to the normal photovoltaics, you know. And it still has a biomimetic aspect. So the sensitizing dye, which I will talk about later, can be, for example, chlorophyll or anthocyanins, for example. These are in raspberries and cherries and hibiscus. So these are dyes which can be used from nature. And another important fact is the DSSC cells can easily be made from things you can find in your household. You can make your own solar cell with toothpaste or paint and some raspberry syrup and a little bit of disinfectant. And it's not a great cell, but it will work. So it's very educational. There are two important things. First, school kids can do that just as an experiment. But on the other side, if you can produce that at home, you don't need clean room conditions. So you can make the cells very cheaply if you think about mass production. So that's an important point because this is what we want. We want a cheap cell, the cheapest cell we can get, which has a decent efficiency. So the idea is, maybe I sit down for the minute. You know, I'm old enough. So this is how the dye-sensitized solar cell is working. So we have light which impinges on the cell. It shall fall onto the dye. The dye, can be the raspberry dye, is excited. And then this is the important step, injects an electron into the titanium dioxide. Okay, I show you how the cell looks like. So there's a dye sitting on the titanium dioxide. And if the dye, after the absorption, injects the electron into the titanium dioxide, we are there. Because that means the cell is working. At the moment we have injected into the titanium dioxide, this is a semiconductor, then we have the diode function and the electron can't go back. And then we can actually just connect to that, and then the electron goes over, we can use it on an electric load. There's a counter electrode, and there's a iodine redox reaction, which brings back the electron to the dye. Because if this wouldn't happen, the dye would be bleached, and then it has captured a single photon and is dead afterwards. So we have to replace the electron here. Okay, this is how it looks like. Maybe I stand up again. Enough recovery here. This is now a transparent glass. It's important. We need electrons on both sides, but we need to get the light in. That means it needs to be a conductive, transparent glass. Well, there are solutions nowadays, for example, this tin oxide, or in our case, it's actually a tin oxide with fluor doping. And on that, we actually deposit highly porous titanium dioxide. So it's kind of a sponge of titanium dioxide nanoparticles. And then the whole thing is dipped in a dye, for example, the ruthenium polypyridine dye. And then on the other side, we just have a counter electrode. You can use platinum, but that's very expensive, so you can alternatively use graphite, for example, and coat that. So this is all you have to do. So all you need is the substances, a conductive glass sheet, and a counter electrode. You can use a pencil to make the counter electrode. And then actually what happens after the dye has captured the electron is injected into this sponge of titanium dioxide, and then the electron has to travel around until it comes to the contact and then can travel outside. And then in the end, it's given back here with this redox cycle. So this is in principle how it works. This is maybe a little bit better to see how it looks like. There are two important facts. These C cells separate the functions which are otherwise provided by the semiconductor material. These are two things. This is the generation of the photoelectron. This is done from the dye absorbs, generates an excitation, and this excitation is then given to the titanium dioxide. And the separation of the charge carriers, and this is done by the titanium dioxide, because the titanium dioxide acts as a diode there, as a semiconductor diode. Okay, so first the dye injects into the photoelectrons into the titanium dioxide. The titanium dioxide is doing the charge separation, and then the electrolyte redox pair completes the reaction again. So we have a full cycle, and this is how it looks like, by the way. This is these titanium dioxide nanoparticles on the left-hand side. This is a scanning electron microscope picture. And on the right-hand side, you actually see the dye. I think this is actually the best working dye. This is the ruthenium dye. This is the ruthenium complex. And these are the antenna complexes which actually absorb the photons. So this is important now. We need a dye which is very efficient in getting the light absorbed, getting an electron excited, and this electron needs to be conducted to the titanium dioxide. If you have recombination there, the dye doesn't work, and the solar cell is kind of a very inefficient one. Okay, some tricks in order to raise the absorption. We use the titanium dioxide nanoparticles. This is a kind of 3D matrix. It has an enhanced surface area, and the refractive index of titanium dioxide, by the way, is, the girls will like it, it's like diamond, so it's between 2.4 and 2.9, very high refractive index. That gives rise to a lot of reflections because of the high refractive index. And there are multiple reflections, and you have more than one chance to get the light absorbed instead of losing it back again. So this is how the titanium dioxide is supposed to work. And if we know, let's be fair, if you compare the performance of such a cell, then the first thing, I didn't even mention that so far, it has an efficiency in best case between 8 and 11%. This is a lab scale. So without the lab, it's not as good. But you see, it's quite comparable to these thin film silicon amorphous ones, which are between 10 and 12%. And they're both not as good as the single crystal versions. This is the one you find on the rooftops, the very expensive ones. Okay, what's the benefit here? 20% efficiency is something you can't beat. The stability is extreme, so even the producers give you something like a 25-year warranty, a 30-year warranty. If a producer gives you warranty over that range, they are absolutely sure nothing happens. You have to wipe them clean. After 20 years, they're still at the same as on the first day. So that's very positive here. The payback time is relatively bad, and the 2 to 3 years actually depends on the country. In some of the countries, you get money for installing such systems. I think Ireland doesn't have a scheme like this, so that means the payback time here is even longer, and shows that they're much more expensive than the payback time on a silicon amorphous system is just 10 months. Even it's just half the efficiency. The price is so much lower than the payback time, which is interesting to us as a customer, is actually below that. Well, the DSS cells are not too bad in the efficiency. The costs are great. They're much cheaper than anything else. But the stability is an issue. So there's no dye in existence which just lives for 25 years. So no chance there. And then you need to think about if you make a commercial system like that, how do you replace the dye? Or do you find a dye which is much more stable than the dyes which are used in the moment? I'm not too bad at the time. So there are some new concepts. One of them is the Graetzel cell itself. This is the lowest point. Just to give you the full, well, maybe not the full, but most of the new developments in solar technology. And this is using nanostructures. For example, you have a pyramidal structure which causes multiple reflections as a nanostructure. Not just a random nanostructure, but a kind of man-made nanostructure. New materials, you can have very efficient solar cells with, if you use gallium arsenide, cadmium telluride, or this copper indium selenide here. Very efficient. I think the best one, we see that in the next final slide, is 43%. But the costs are not just twice as high, they are 20 times and more expensive. So you need to combine such a technique actually with this here concentrator cells in order not to cover such a huge region. You want to have a big mirror or small microlenses which focus on a much smaller area. Therefore, you don't have to make such a big cell. And other techniques are quantum dots, for example, surface plasmons. Oh Jesus, I made a typo in my own domain. It's surface plasmons here. Okay. Concentrator cells, I already spoke about. They're MIS cells. Instead of a p-n junction, you have a thin oxide semiconductor cell. So you see there's a whole range, and that's not even complete, of different developments. So all of the cell types try to get better in the future. And maybe as one of the final things I'm going to show you here, oh yeah, we have some examples here even. This is the nanostructure. These are the quantum dots. You see you can tune the absorption of the quantum dots nicely with their size. These are these concentrators. They are huge factories. You know, this is a concentrator plant here. Now in this case here, there are hundreds and thousands of mirrors, and they focus the sunlight to this point where there's actually a steam generator that generates electricity. So it's not even photovoltaics, but you can use this concentrator concept to make high temperatures, which are needed for conventional turbine technology. So this is now the highest efficiency, or the highest efficiency of photovoltaic cells. And since this one lost its energy now, I have to point with my fingers. Okay, 2-3 things maybe I should. You see there's a whole different zoo of technologies here. This is the most, see that this is old, so this is 2006 or 2007. This is what's the best was 40.7. These are these multi-layer cadmium and gallium arsenide type cells. They go up to, in the meantime, 43-44%. But they are so expensive that they're nearly prohibitive. So what you want to do, this is the Graetzel cells, this orange here, and this is around 11.1% at the moment. And if you compare that now with these thin film technologies, cheap technologies, they're not far away from that. You see, going up to this point, that's just 12%. So very near and much cheaper in comparison. So I don't say there's a single technology which is already much better than anything else. So I think we have to continue research on all of this to see what works out best at the very end. Okay, so now the most important point. I think we have a break first, and then we have the discussion, hopefully. So thank you very much.